So once again, hello and everyone. Welcome to the seminar series AI for Predictive Maintenance. I am Madhav Misra and I am hosting this seminar series. I have honor to introduce Dr. Abhinav Saxena from GE Research, San Ramon, California, who will present the seminar on the topic of using AI and machine learning in improving industrial reliability through predictive maintenance. And I can give a brief introduction about Abhinav. Dr. Abhinav Saxena is a principal scientist in AI in and learning system at GE Research. Abhinav has been developing machine learning and AI-based PHM solution for various industrial systems like aviation, nuclear power plant, and healthcare at GE, and has been driving integration of AI-based PHM analytics in GE industrial system. He is the PI for ARPA GE MENA program on AI-enabled predictive maintenance, digital twin for advanced nuclear reactor. Uh, yeah, he will give a brief about himself, and after the presentation, we can take some question if we have. So, Abhinav, the floor is yours now.
Thank you, Madhav, and good afternoon, everybody. So, Madhav, can I go ahead and share my screen?
Yes, please. Yeah. So I have stop now. Yeah, please.
Can you see?
Yes, we can see, but it's blank now. At least I can see the blank. Yeah. Yeah. Now we can see. Perfect.
Okay. All right. So, good afternoon, everybody, and thank you, Madhav, for inviting to this seminar series. So, hopefully, I will be able to give you guys a good uh, view on the type of algorithms, methods, and applications that we are focused on. So I'll give you a glimpse of some examples of what we have been doing, and then since I come from GE Research, I will be talking about what are the research questions that we are going after. So having applications is great, but there are always challenges and how we are solving those. And if you like, please feel free to interrupt me. It's totally fine. And you can also, so if you raise your hands, I won't be able to see it in the presenter mode, but feel free to speak up, please. All right. So I'll give you a little view on what GE research is. So GE, a lot of us know a lot better, a lot more, but GE research is relatively unknown. So we are a corporate research entity, and we work with all different GE businesses. Be with so those businesses being GE Power, GE Aviation, and renewables, healthcare, all those. And we used to have many more. And as things are changing, the portfolio has been shifting. But we do a lot of problem solving and applied research for our businesses. In addition to that, we also work very closely with our government partners. So we apply for government grants, just like any other research institute, and then we execute on those. And then we also have a lot of strategic partners, which include universities or research labs or different organizations. And now something about our group. So I am part of the artificial intelligence group. Our group has existed really for more than 30 years now, and I mean it's been in existence from the time when machine learning and AI didn't even used to be a thing, or such a buzzword that it is today. So and the name of the group has changed from data science, machine statistics, machine learning, and whatnot. But really, if you see the type of applications we work on, they dig into the heart of the current AI and machine learning approaches. So we do work on medical images or natural language processing, diagnostics, prognostics, health monitoring, of course, is our bread and butter, and then AI-based optimization and controls of workflow and automation, and of course, the science of AI is what we call it, is the key gaps as we see in current machine learning and AI frameworks. from our industrial applicability perspective. So robustness or common sense reasoning or explainability are some of the key themes. All right, so predictive maintenance, and I'm not going to spend too much time on this chart because I understand that you all are connected to preventive maintenance or ideas related to that. But what I would like to just emphasize on this is the significance of another buzzword that you may be hearing is called digital twin. And how is digital twin, whatever we are doing under that umbrella is different than anything else that we have been doing, right? So as we follow through this trajectory, CBM, PHM have been the talk of the trade for last maybe 20 to 20 to 30, 20 to 30 years. So PHM relies on, for instance, building models of your system, how they are approaching degradation, and then once we detect degradation, how they approach a certain threshold beyond which we say they are not going to function as we expected them, right? But if you really look at those models are usually statistics based. So we have sometimes statistical distributions about failures, bathtub curves, and those kind of ideas. And then the performance that we get out of these systems is also valid on aggregate basis. So if I had 1,000 jet engines, yes, I can be about 90% right about that if my methods are right. But then that's really not what the customer is interested in, or we are not interested in. If I am taking a flight, I'm really interested in making sure the reliability of this particular jet engine. And that's where the idea of digital twin comes in, where uh, it's a model that specifically adapts to a particular asset. So if I have 1,000 copies of physical copies of that asset, then there will be 1,000 digital twins that are, or the models that are adapted for that particular asset. So, and another thing that's different with digital twin is it's a continuously learning model. As our assets change over time, uh, they the characteristics change, and then we expect that our model should catch up with those. So, model should really represent at any given time how the current asset is operating, and that's the idea of digital twin. So, it's a more precise or precision uh, maintenance policy that when we can craft around these assets, and that's why I wanted to emphasize on the idea of digital twin that has been going pretty strongly in our world. Just a glimpse of as part of motivation, and I alluded to that a little bit earlier, that the portfolio for predictive maintenance within GE ecosystem is quite wide. So we look at all of these different kinds of industrial assets, and they're all uh, associated with many different challenges. So some of these assets we cannot communicate in the real time, right? Or some of these assets they are located in so remote locations that getting data from there becomes very difficult. Some assets like renewable wind turbines or offshore wind turbines, we can get data, but the assets are operating in such harsh environments that sending, because when we determine that we need to do maintenance, we still need to send somebody out there, and those environments can become so harsh. So that's brings another set of challenges. Uh, Data as they collect from these systems are very different. If you talk about aviation, we collect mostly something what we call a snapshot data. So every flight, based on some predetermined triggers, we would take 5 or 6 snapshots of different sensor values within that flight. Now you can imagine if I'm taking some data from a vibration signal, and even though the actual vibration signal or accelerometer on the airplane could be in kilohertz, could be measuring the vibration in kilohertz, when we take a snapshot, the snapshot is some sort of an aggregate, and we get is, let's say, a mean value, or the first few frequency bands of the amplitude. Now, it does have useful information, but it may not have all the information that one could, derive by analyzing the full flight data or full resolution data. So we get only 5 or 6 snapshots per flight, and then we have data from 1,000 flights. How do we make sense of what is degrading and how fast it is going? If you think about renewables, the data that comes from that system is already a 10-minute average. That's the industry standard. So it's a scatter data. They collect data and they send only 10 minutes average data. So there are many different kinds of data modalities that we get, and resolutions are very different. And the challenge is how to, but the key theme is the same: to keep the assets running, to not incur any downtime or unplanned outages, and of course, in some of these systems, to keeping them safe. So again, this chart exemplifies the number of assets that are currently or anytime they are operational. So, and the scale is just huge. We talk about thousands of gas turbines or thousands of CT scanners, engines, wind turbines, oil and gas equipment. So the key message here is that although AI has made a lot of developments, a lot of advancements, but the type of assets that we deal with, we call them as critical infrastructure. So we cannot afford failures in these systems because the consequences are very high. And then these are also prime targets for bad actors. So we have to also guard them against cyber attack. Um, they are very long um, field life. So some of these, and actually I have not even listed nuclear reactors here. I mean, they are built to last several decades. And in fact, some of the plants or systems that sometimes deal with, they were built like 60, 70 years ago. They have instrumentation, they have sensing, but we cannot afford to completely replace that sensing. We do keep adding new sensors, but then just by adding sensors, you don't solve the problem. We have to also have the data management systems, the data flow systems, and all those things have to be upgraded as well, which sometimes are not cost effective from customers' point of view. So, and since these systems last for a long time, the environment around that, that keeps changing as well, and that's why having a digital twin idea, it really works for these, because as systems evolve, the twin or the model needs to get updated as well. And they are very capital intensive systems, and it could take millions of dollars if for repairing of some of these, and as well as the downtime, and the productivity that we lose can be very, very detrimental too. So where does AI come into all of these? And I've listed some examples here, as so as to, and these are not inclusive of everything, but most of the things that we are working on in our groups. And we have a large organization dedicated to these methods and these problems. So for instance, images and videos, they are quite widely used in our world. So for industrial inspection, aerial inspections, or video intelligence. So for instance, we have these offshore wind turbines which are out in the ocean, and obviously it's not possible to go and physically, or for humans to go. So we send drones which actually go and rotate alongside while the turbine is blades are moving, and try to take videos or images. Then comes but then just taking or gathering all those images is not the problem solved, because more data you collect, more you have to analyze as well, and that creates another challenge. And then different lighting conditions, different weather conditions, how do we calibrate for all those to say that this is some defect that we saw on a wind turbine blade number 3 on that particular day, and 6 months later, is it exactly the same location, same blade that we are observing? And given all the variations due to lighting and all the and all other weather conditions, how can we go back to the same spot and identify whether that defect has grown or not? So there is a lot of work going on in images and videos. Natural language processing is yet another important piece. These systems are complex. A power plant, some of the power plants that I have seen, they could have up to more than 30,000 sensors sensing different kinds of things. Now, where these sensors are located, how are they connected? If I build an analytic on this particular sensor, and there is another algorithm that is working with some other sensor data, how are they connected? So all those, if we, so the people who are operators or who are on the ground, they have developed this operational knowledge or tribal knowledge that they are able to, uh, make sense of a lot of different things. But when we talk about algorithms and data, there is a need for all this information to be organized in some sort of knowledge base, so that can be used for contextual reasoning. So a lot of information is actually stored in free form text, uh, starting from the design documents to operational notes and maintenance procedures and whatnot. So all of those, how can we take that and automate some portions of that processing pipeline is what we do in this particular bubble. Time series, of course, we do a lot of forecasting, detection, diagnostic, prognostics. I won't spend much time here right now on this. Robotics, again, we are developing a number of different kinds of robots that can go into um, environments where humans cannot go. Another example, we were just looking at it a few days ago. Uh, so wind turbine blades, they are huge, and but right now the inspection methodology only involves looking at those blades from a distance through an IR camera or a regular camera, but that doesn't necessarily give us a very complete picture. But then we've developed a robot that can actually go inside the wind turbine blades and go inspect the whole surface, um, and beam back images. In fact, a lot of processing happens on the edge on the robot itself, so it only beams back images, um, that we suspect or the robot suspects something is going on. Um, there are other examples where we are using robots for actually carrying out some repairs. Um, so, so yeah, robotics is yet another way of applying some sort of maintenance processes. Then science of AI, and I'll dive deeper into that. So robustness, explainability. Now we have all these algorithms, and we all measure the algorithm performance in some sort of accuracy, precision, recall, or F1 score, and those kind of things, right? False positive rates, false negative rates. Um, Even though these numbers might look great on paper, the consequences of those false positives or false negatives can be very, very high. So how do we bridge that gap? How do we know where we can trust the machine learning model as it is saying and make a decision based on that? Or do we need to ask help from a human expert that in this particular case we cannot really decide, and somebody actually needs to either collect more data or do something different or something more before something or definitive decision can be taken. So explainability, and continuous learning, all those aspects are still somewhat of a research question that we are dealing with, and ultimately the goal is decision automation. And there are many different ways where automation can play an important role. So of course, optimization and controls of how systems are operating, reconfiguration if something is not looking very healthy, can we reconfigure so we don't have to take the downtime right now and let the asset operate with partial performance, but at least until the next planned outage. So opportunistic maintenance and workflow automation. So opportunistic maintenance refers to, if we are already going to do a maintenance on a particular system because it needs, or it is degrading to a point that it really needs maintenance, what else can we maintain in that same trip, right? So if there are other things which may not have completely degraded, so it kind of goes like an opposite idea to prognostics, where we only want to maintain where things are going towards a threshold. In this case, we also want to maintain things which are strategically located in that same spatial region, so overall maintenance, is optimized. And then workflow automation. So all of these are many different use cases or applications where AI technologies are in use currently. Any questions before I go into some examples? Right. So I'll present to you two or three examples here, and then I go into the more research themes. So one, and these are mostly deployed examples or solutions. So they are fairly at a high level of maturity, and they are actually currently working on the assets that GE provides services for. So one thing we talk about is virtual sensors. So let's talk about a jet engine. And a jet engine, if you really look at it, the physical sensors, we have very few physical sensors, less than uh, 2 dozen sensors on this whole jet engine. But to keep a track on the health of this engine, we need to sense, or we would like to sense a lot more. But the environment gets so hot and harsh that these sensors themselves become a problem, because when a sensor is failing in that environment or not, that becomes yet another issue. So what we rely on is what we call virtual sensors. So we have physics-based models. So think of these as Kalman filters or particle filters, which are sensing the internal states of the engine in real time, right? And then those data are then used for building your fault diagnostics models, or even degradation propagation models. So we use those. So given a set of physical sensors, we derive many other virtually sensed parameters, and then together these all feed into the machine learning based early warning predictions. So the goal, really, when we talk about prognostics, we think about a bearing or a gear starting to degrade or fail in some ways, and then eventually reaching a point where it can no longer function, right? And we want to wait until that time to service that. But in reality, that doesn't really work, or that scheme doesn't really work well, because we cannot really schedule maintenance for each and every component when it wants that maintenance, right? So some level of optimization that needs to happen as we identify about different components and different and the health of those components at any given time, and then take all that information in conjunction with the scheduled outage planning, or when the opportunity is, and then optimize the overall cost along with that information. So, for instance, if an airline is flying into where it's into an airport which is the hub for that airline, yes, scheduling a maintenance in that particular location for that engine makes more sense, rather than letting that engine take another flight just because it has more life left in it, right? So all those things need to be optimized. And in our world, really, early warning is the name of the game. So if we can provide early warning such that those planning or operational planning can be included in that, then only it makes sense. Otherwise, yeah, even if I tell with high precision that this is the, let's say, health of the bearing that needs to be replaced, and we happen to be in a remote location, it really doesn't help us save money, or keep it uh, cost economical. So again, uh, some metrics are shown here. I mean, for instance, we say 30 days early warning or compressor issue. Now, 30 days is not always achievable, but this is just an example. But the idea is we need to have at least 15 to 20 days of warning before something can be scheduled properly in time. And different systems have different types of time scales. So when we work with our customers, the metrics are set ahead of time. And that's one of our questions, that how much time early warning can you get? And at the end of it, the answer can be, well, this cannot be done. If they said we wanted 2 months of warning, we say, well, this cannot be done because the data just does not have that observability, or the fault grows much faster. Well, then they need to understand that as well. So next application is on automated inspection. And again, these engine blades, they have a coating on it, and with the usage over time, this coating tends to degrade. So again, and inspecting these blades manually, time over time, is a very time-consuming process, and that's how it used to be done. But now we are using technologies like automated boroscope inspections, where think of, we have a camera pointing at these blades in a certain angle every now and then there is an automated machine learning vision algorithm, which is identifying which of these images are likely to have damages. Whether it has damage or not, that will still be confirmed by a human, but at least the out of the thousands of images that we collect from a particular engine, we can just identify a subset that can be reviewed by the humans. So there is some automation there, and once somebody okays, uh, or quantifies the damage, then that information feeds back into the coating lifing type models, and you can be estimating. So these are, again, think of them as degradation models that are being updated by some inspection information, right? And beyond that, because these systems or these they take long time to develop for in these engines. So the next engine program can take that information into account, and maybe even improve design, as we go to the next generation systems. Now, if you think about applications like uh, wind turbines, new designs are coming out every 2 or 3 years, because there is so much innovation going on. And in that case, that design loop, or that cycle, is even faster. So anything we can learn from the existing systems, we can feed back into the design, and improve that, or design out that issue. I had mentioned use of natural language processing. Again, on the left hand side, I'm showing a form that gets typically filled out, and you can see that it has a lot of lines and tables and handwritten notes, sometimes crossing different lines. So it's a very challenging problem to identify what's actually was written, and what are the pieces of information. And if the shape and size of this form were to be standard across different plants, let's say if we talk about power plants, then we there was still some hope identifying, which portions of this form to look at, where the information is. But if you really look at it, it varies from customer to customer, and even location to location. These forms could look very different. So it becomes a challenge in how to extract that information. So we are working on a number of different methodologies, where we take these forms, digitize those, and then build models, or language understanding models, from those data, to derive a number of different outcomes. So we have, let's say, operational history for 50 years from a plant. Well, that history is useless or meaningless, because who has time to go through all those records, and label or tag those records with what type of failure modes they had, what was done, which uh, what worked, what didn't work, and those type of information are not readily available. So if we can use machine learning and AI to read through these documents and extract those, labeling that data becomes the first question, or first step, before we can even train those models to do something automated. So there is a lot of work going on, and sometimes we try to make use of uh, models that are freely available, the language models. So let's say the BERT model that Google open source some time ago. But a lot of times, because this language is not like complete English, and there are certain words have specific meanings, we cannot solely rely on those models. So there are a fair amount of let's say fine tuning of those models that needs to be done. So that's another key focus of some of the programs that I'm working on. So from here, I will switch gears, and let's see, we have about half an hour, 15 minutes, let's say. So what I will go into, some of the challenges as we perceive in the predictive maintenance, from the AI's perspective. And there are many, as I list some of them here. Uh, but two that we are currently focusing on is explainability and uncertainty and trust. And so I'll uh, dig a little bit deeper in some of these. So one of the problems that we often deal with is, so I have a jet engine and it only had, let's say, 20 or so sensors. Uh, and when we do virtual sensing, the number of sensed parameters shoot up to approximately, let's say, 300 or 400. So now we are monitoring 300 or 400 parameters. Then we have environmental data and whatnot. So actually, the list that I get from some of our engine lines is about 540 different channels of data. Now, if I knew uh, that a particular so think of an engine as a tube, and it's a 3D environment. And if a defect develops on one side of the engine, if I knew where it would be, I could just use sensors in that area. But in the beginning, I don't even know, where to look. So we needed a method. What we and this approach is called what we call as unknown approach. That we don't know what will be the defect. We don't know how observable it is, but do we have a chance for catching that? So in that, we built this is a deep learning model that we built, and it has some characteristics that we think are important to model within time series analysis. So there has to be a notion of temporal patterns. There has to be a notion of how things are connected or correlated in the physical sense, because the temperature and the pressure, they have to have a certain relation if they are coming from the same portion of the engine. So keeping all those in mind, we designed this particular neural network, and the advantage with this is, as a byproduct, it gives us a correlation matrix or a causal matrix, as we call it. We call it causal because it's not instantaneous correlation. It's a correlation derived over a certain period of time between different parameters. So and this matrix gives us a view into what the model is learning from data. So we are not teaching the model any physics, but we let it learn from data, and the data. And then once we get the causal matrix, we can go back to the domain experts and ask, hey, the model has learned these relationships. Looking at the data, do they make physical sense? And some of those we are able to clarify, or with the domain experts. Sometimes it is the artifacts in data that the models tends to learn, but getting access to domain experts, we can fix those errors and improve on those. And in some cases, some correlations or some causal relations, they don't really make fully sense, and we can manually update those, and essentially arrive at a graph that we all understand, that should make sense. Yeah, so the bottom is really how the pipeline works. So we have a lot of uh, data, historical data. We create smaller samples of it for training the model. The model trains on offline, with that uh, historical data, and then we get a test sample. So this is the type of causal matrix that we get out of the model. Then we get a test sample, we run it through the model, look at the residuals, and where those residuals are coming from. So model is also able to tell us which parameters are really causing these high residuals, and that allows us to do some diagnostics downstream as to what is really going on. So to give you an example, here is a system, and it's an aircraft jet engine, and on the x-axis is the time history, and this is about, if I remember correctly, about 2 years worth of data. So the time axis is about 2 years long, and these are all the model parameters. So in this case, I think we had about 200 or 50 or so parameters as part of the model. And as you can see, there are different parameters. They start to trend anomalously for a certain period of time, and there are many different locations here where the maintenance was actually done. In this case, I'm not depicting that, but maybe there was some maintenance done over here, and then this issue went away. But then there are certain issues that appear more systematically than these intermittent ones. So, for instance, you can see these streaks over time that are starting to show up. And this was an issue that was developing over time, and it took more than a year to develop that. But looking back in historical data, we could identify that, if we had a method like this and a visual like this, we would be able to probably avoid that event that was not. I mean that we wouldn't want it to happen. So ultimately, looking at all these parameters, we combine those into a single global anomaly score, and as typical anomaly score, depictions, the score would go up, and then we would have a threshold, and at certain threshold, we would know what parameters are causing these, and that helps us identify and diagnosing. So we have more than 200 different analytics monitoring a jet engine at any given time. So this method is really not geared towards any specific fault mode. This is more a generalized method looking at the system as a whole. And so if there are issues that are not caught by other analytics, then we hope that this system will be able to find it. And on the other hand, if this system indicates something and there are other analytics that are also indicating similar kind of issues, so it's more like a validation. So but connecting information from these different algorithms it becomes a huge digitalization challenge, that we have solved to quite a good extent, but new issues keep arising. So yeah, it's not completely done. So this is just a visual of what those causal matrices look like. So if we learn some those causal relations from the fleet data, from historical data, so let's say this is what the matrix looks like. We can go into specific cells and say whether this parameter is a causal parameter for this particular one, right? We can do all those, the validation that I was talking about. But when some anomalies start to appear in the system, the same asset, the matrices, they look very different for that local time period. And it is this difference that we rely on in identifying which parameters are really causing you know these to go anomalous. Whether we know the root cause of why those parameters are behaving like that, in some cases we do, and we indicate that. In other cases, we just send a notification to the operators that these things are looking anomalous. Can they go take a look? So for this particular method, there are a number of examples. Aviation one, I briefly talked about. We are currently working on a nuclear application where there are so many different components in the balance of plant. So we are applying the same method to many of those. Wind turbines is yet another application where we have applied this method to detect unusual weather conditions with respect to the turbine. So we sometimes when we design these turbines, we have an estimate of or historical averages of what the weather could be, but there are times when unexpected conditions happen, and being able to detect those not only allows us to protect the asset under those from those environments, but also design our next generation of assets that is able to withhold that withhold those kind of conditions. So yeah, so there is a lot of different application examples where we are applying these type of methodologies. Okay, any questions? All right. So one last piece I'll talk about is about trust. And really the question is, uh, if our model is saying something, are we sure that we understand the model is saying something right and it's not an artifact of data, or just because the model didn't really learn? And here are two examples where, let's say in a wind turbine case, um, the model is able to tell us that, yes, I know that this is a fault class one, but please, and because I'm so confident, you go ahead and schedule some maintenance or whatever the appropriate action might be, right? But then uh, there could be a scenario where the model should be able to express as if the wind turbine generator might have fault one or three, but definitely not two. So to confirm, we need more evidence to resolve the confusion. So here the model, we call it the humility in the model. That model, when you ask the model, can you predict about this? Uh, uh, Traditional machine learning model would always produce a result and may not tell anything more about it. What we want is to wrap this layer of humility on all our machine learning models. So the models are also able to express how confident are they of what they are predicting. Likewise, on the healthcare side, is an ultrasound machine, and the model might be saying the patient has symptoms of disease X, and here is the evidence. I'm very confident, and you can begin the treatment. Whereas there might be a scenario if the model might say, "Hey, I don't even know what this disease X, and can you? I mean, the technician or the doctor a radiologist has to really look into it." And these scenarios happen more often than you would think. These systems, they are operated in environments, very different environments all across the globe, different type of operating practices, maintenance practices. So keeping all those in mind, how do we give that additional information or capability to our model so they can make those judgments? So we have been exploring something called epistemology approach, and essentially, I will not go into details of here. There are some paper references that you can look at, but essentially, what it does, it looks into the layers of neural network and tries to understand, how close my current input sample is, to the training data that we have seen. Now one could also do that comparison in the input space with the training data, whether our data is coming from the same type of distributions or has it changed. But in the embedded space, sometimes that comparison becomes a lot more clearer. So we have come out with a certain ways on how to extract that kind of evidence of being in that uh, normal input space or not, and that allows us to express some confidence whether the model knows, or it may know, or it may not know, right? And accordingly, the every prediction is dealt with that additional piece of information, and accordingly an action is taken. So currently we are in the process of applying it to optimizing wind farms. So sensor data comes in, and this machine learning model is is able to identify whether the model as learned is capable of predicting in this current scenario. And if it is not, then the model is also directing us, so what is the next best step. So it might say, well, it looks like we are very close to predicting correctly, but I think we need to collect more data, and it just sends that log to the operator. So next time those conditions happen, we collect additional data and improve the model further. And whereas in some cases where it is making predictions, the actions that are already decided, and then we go and deploy that, or apply it through the controls for the wind turbine. So there are many different ways in which we can learn based on this methodology, and few of them we are showing over here. So for instance, self-learning is you can collect more data, at that for that particular wind turbine, update the model, Or you could look at the wind turbines which are close by in that same farm, and maybe they know how to deal with that situation, or so use data from those, or even learn from simulations. So all of these assets, we have very high fidelity simulations that we can generate data. It's not possible to run those simulations in the real time while we are monitoring these assets. But once we know that this is the region where the model lacks understanding, we can then offline, simulate more and update the models. And as you can see, this idea of continuous learning, is very prevalent in all these scenarios. So as the wind turbines are operating, these models are making predictions. Over time, these models keep updating. What we as humans have to do is, at this point, every learning event is has to be okayed by an operator. So because at times we run into situations which were anomalous and data looks different, and sometimes model might think, hey, this is a new regime that I need to learn about, and might trigger a learning update, but we don't really have to react to every such scenario. Yeah, so I think this is my last chart. um, all I would conclude with this, that machine learning and AI has advanced PHM methods to a big extent, but then there is a number of challenges that still remain. And although we can borrow from AI and ML research that's going on, all around, there are a lot of things that we need to solve. If especially for company like ours, where the applications are to those critical assets, and uh, the data quality and all those are not given as we have in the consumer world. So yeah, a lot of avenues for research. So with that, I'll stop and I'll take few questions if we have. We have yeah, about 12 minutes left.